All right. Welcome, everybody, to the first class that's in session for me. If you guys don't know, I am a physics and astronomy teacher. And it got to the point with the COVID, all that stuff, that we are going to be teaching from home. So if you guys are interested, make sure that you guys follow, subscribe, all those things, so that way you guys can keep up with what we're talking about, not only here, but everything else. Make sure you share it out. Hopefully, this will help not only the students that are in my county and in my area and my personal students, but hopefully it'll be able to be out there to help anybody that might need it. So that's what we're going to be doing today. We're talking with astronomy. We're talking about the brightness of stars and the color of stars. And so our objective for the brightness of stars section is it's chapter 17.1 in the astronomy book that we use. The objective is to look at understand our difference between luminosity and apparent brightness, as well as to figure out how astronomers actually use brightness with the absolute magnitudes and stuff like that, and what all of this stuff is. So make sure you guys get your word pad open, get your notebooks out, and let's jump right on into it. So luminosity, first we have to have an understanding of what luminosity even is. And that's the biggest thing, right? If we're going to talk about these things, we got to know what's going on. We have to understand what it is we're talking about. So luminosity is the amount of energy at all wavelengths that a light source emits per second. That's basically saying that if I take every single thing, all of the energy that's being shown up by a star and it's being shot out, the luminosity is how much is being thrown out at you, how much light is being thrown. And that's what luminosity is. Now, astronomers actually express luminosity in for other stars in terms of the sun, meaning if we take Sirius, which is the brightest star, it is 25 times that of the sun, as in it is 25 times brighter than the sun. It big bright boy out there. The way that we would write this if we were talking about it is 25 L sub sun. And so it would just be the big L is for, oh man, my camera's mirrored. Big L would be for luminosity, and we use the sub sun to talk about the fact that we are talking about the sun. And that's just a nice little way to label it out. So, all right, apparent brightness. Okay, so what are we talking about here? What's apparent brightness? Well, thing is, before we get into what apparent brightness fully is, and I realize that I'm blocking that a little bit with my webcam. I'm sorry, I couldn't figure out a great spot to put it. Now, stars distribute the same amount of radiation in every direction. It's perfect. It's uniform. It sends it all out equally in the same way. So the thing is, it comes up to us, how could we possibly quantify how much reaches a specific spot? Well, that's weird and that's tough. But the thing is, what we have to do is we have to go off of what we call apparent brightness. It's the amount of a star's energy that reaches a given area each second on the surface. So how could this help us? Because the thing is, if all the luminosities of every single star are the same, that would mean that apparent brightness should be very easy to figure out, and we should be able to have no problem with it, right? And it shouldn't be any weird things. Well, if it was the same, then we could actually determine distance of these stars and how far away they are from us just based on the apparent brightness, because we understand one thing. We remember that we talked about a long time ago in my class, and for those that are watching this for the first time and have no idea of what I'm talking about, we talked about an inverse square law. So an inverse square law basically saying that the farther light travels, it covers an area that's proportional to the distance traveled squared. So, meaning, if I have something that travels twice as far as it normally would, that means 1/4 of the amount of light will be shown in a given spot in that area. So if we have Earth is one distance away, we get all of the light normally. If Earth was moved to 2 distances away, we would get 1/4 the amount of light that we normally get, and so on and so forth as we continue to go. If we get to like 10, if we're 10 Earth distances away, we have 1/100th of the light we would normally have. And so that's what the inverse square law is telling us with reference to light. So if we can tell how much light is coming in on our planet, we can determine how far something is away if it all has a uniform luminosity. It all has a uniform amount of energy that's thrown out from it. Thing is, that's really great. It's wonderful. We could learn so much. We could know how far every single star is in the sky based on the light radiation alone that's coming down to us. But thing is, all stars do not have the same luminosity. And that's wonderful, because it would be really boring if every star was exactly the same. Thing is, our universe is so diverse of a place, and stars are so different and so crazy, that gives us a lot more to study and actually leaves us further with more to do entirely, which is an incredibly exciting thing to look at and to understand with what's going on. Now, it does mean that we have no idea how close something is, or if it's just a low energy star. That's the downside. We have absolutely no way of knowing how much light is coming from that, and if that amount of light is because of the amount of energy that we have, or if it's how far away the stinking thing is. And we're not sure about that. So to measure the luminosities of stars, we actually have to compensate for the dimming effects of the distance. But if we don't have the distance, then we can't do that. We can't actually find all of those things. We can't find out how far something is away easily. It's so difficult to do. I can't just go, yes, Sirius, that's about 7 light years away. That doesn't happen. You can't just look at it and be like, I know, and now I can figure out how bright that star is. And so that means that we have to find things, and we have to base it off of apparent brightness. It's based off this idea of how bright is it for us to realize and for us to look at. If I'm looking at the sun, it is super duper bright, and so it appears very bright to us. But if I look at the night sky, the moon, which is reflected sunlight, is less for us. I have other things that are less, and it stinks, right? Because we have to go by this apparent, which is incredibly subjective in the first place. We have to decide, oh, you have about this much light, which then comes down to how do we describe this thing and all that. So do you use stars for comparison on determining distances, or could you? We could if everything was uniform. If every star was uniform, we could determine the distance. Yes, it would be possible to do that because we would know the same amount of energy is being output. But it's like having an equation, right? Let's take A equals B plus C, right? Well, I could know what A is, but if I don't know what B and C are, I can't solve it out, right? Like I can't know everything. Or if, let's say I know B, but I don't know A and C. Well, I can't get my answer, and I can't figure it out because I'm missing 2 variables. So we can know about how much energy we're receiving, which is our apparent brightness. We understand how much we're receiving, but we don't know how far away it is and how much energy is being output. So we're missing 2 parts of this big equation, so we can't actually figure it out. But if we did have a uniform luminosity, if it did have this uniform amount of energy that was just thrust out of the dang thing, then we would be able to determine how far every single star is away, which would be spectacular and amazing. But we can't necessarily do that. And so we can't determine stars and how awesome these stars are and how amazing they are based off of just their luminosity. Because we would be able to tell, oh, this is a high energy star. Oh, this is a low energy star. And we could have a better diagram, have a better understanding of where these stars would fall on a line and on a graph if we could do that. Sadly, we can't do that, which is annoying. But we have an apparent brightness scale, a scale that we use as to how these stars appear to us, and that's how we have them labeled out, because we don't have a definite distance, and it's incredibly difficult to find distance based on these things, because we don't know how long they've been traveling. We can't use a velocity equation. We know how fast light travels, but we don't know how far they've traveled, so we can't determine the time. We can't determine how much time it took for that to get to us. So it is incredibly difficult unless we can send something out. And thank you, Frostfire, by the way. So that moves us to our magnitude scale, right? So the process of measuring the apparent brightness of a star is called photometry. And photometry started with Hipparchus. We talked about Hipparchus a long time ago. Now, he had this idea of magnitude in 150 BCE. And he prepared a catalog of nearly 1,000 freaking stars that not only had their position in the sky, but it had what he called their apparent brightness. Now, how could he have done this when the telescope wasn't invented until the 1600s? He used his eyes, which, as I've talked about in my class before, using your eyes to determine something that's up in the sky is incredibly inaccurate. Our worst instrument we have to look at the stars is our eyes. It sucks. I mean, look at me. I have to use corrective lenses. The corrective lenses already mean that my eyes suck. My roommate doesn't have to use corrective lenses. His eyes are better than mine. In comparison to his telescope, his eyes suck. Because we can't see the resolution, we can't see the detail that we need to have. And we're going to talk about why that kind of sucked for Hipparchus later on. But what he did do is he sorted out these stars into 6 main categories, which he called magnitudes. Now, the brightest stars we have were called first magnitudes, and the faintest stars that were the faintest, right, that we see as very low, were considered sixth magnitude stars. Now, astronomers in the 1800s tried to make a scale that was way more precise and better used to establish how much a sixth magnitude star was and a first magnitude star. So we had it before that we could see what the difference was. We wanted to be able to understand what is the difference between something that's this faint that's considered sixth magnitude and what's considered a first. With the measurements made, a first magnitude star ends up giving off about 100 times more light than a first magnitude star. Sorry, I think I said that backwards. A first magnitude star gives off about 100 times more light than a star that's in the sixth magnitude. So if we got tiny little sixth magnitude star, it's giving out 1/100th the amount of light that anything else is giving. And so the first magnitude is so super bright in that comparison. In addition, they also decided that these stars should have decimal classes, so 2.1, 2.2, 2.3, etc. And so these ideas were to subclass and subcategorize these stars so that way we would have a better understanding of where they kind of fall. And okay, well, it's a 2. It's not really quite a 2, but it's not a 3. It's kind of like halfway in between. So maybe we should make it a 2.5. It was a way to give us a better understanding and a better idea of what was actually going on and to better classify these actual stars. So, question really probably becomes, why do astronomers continue to use this system that is incredibly outdated and is from more than 2,000 years ago? So even though we have plenty of other different ways and common ways that we actually use it and to find these stars and star charts and books, thing is, the brightest stars, even our first magnitude stars, we know that they're not even identical. Sirius, which is the brightest star in the sky, sends out 10 times more light than the average first magnitude star, which is problematic for us, right? We're using the system that has it there, and it's like, well, so it's like, why are we using it? Wow, that really, okay, no, that did put that where I wanted. Sweet. So on our modern scale, which by the way, we use this scale because I think it's in the notes, but I'm going to say it anyway. We use it because it actually helps us with books and star charts. That's why it's used. I think I said it. Yeah, I did say that. So, why do different astronomers use different ways to chart stars? It's based off how they learned how to do it and what they chose to do. It's also based off different spots of the planet. If you're in the northern hemisphere, you might chart it in a different way than somebody in the southern hemisphere because you guys have different points of recognition and understanding where it's at. So, all right. So this is our modern scale down there, right? Down there, like over that way, down there. That's our modern scale that we have for this. The modern scale, Sirius has a magnitude of -1.5. So that's how bright it is in the sky based on how we have decided what a magnitude is in our current day. That is our apparent magnitude of it. Brighter objects like Venus actually have lower magnitudes. So Venus, its magnitude is -4.4. And so it's brighter. Our sun, as it appears in the sky, has a magnitude of -26.8. on the scale, being the brightest thing in our sky, right? So that is what its apparent brightness is. Now, the thing to remember is that the larger the magnitude, the fainter the object. So if we look there, the Hubble and Keck telescopes limit has a apparent magnitude of 30. That means the faintest thing they can see is something that has a magnitude of 30, which is, take how bright the sun is and then pretend that it's that, and then like flip it into faintness, which is a weird concept, right? But it's something that is so barely visible that they can see. Now, the faintest thing we can see with the unaided eye is just past a magnitude of 5, just to put an understanding there. So it's something that has a little tiny bit of light. Now, finish up this section. Other units of brightness. Again, sorry, I know it's like right behind me, but other units of brightness. So the magnitude scale is still used for visual astronomy. Thing is, in radio astronomy, no equivalent of the magnitude system has been defined. They didn't make one. Radio astronomers actually measure the amount of energy being collected each second by each square meter of a radio telescope. And they express that brightness of each source in terms of watts per square meter. Infrared, X-ray, and gamma ray astronomers, they all use energy per area per second as their way to measure this brightness. And all that being said, astronomers actually distinguish between luminosity and the source and the amount of energy that happens to reach us as their ways to talk about it. Yes, that's my roommate's dog. That's Charlotte. All right. Now we're on to section 17.2. Halfway through our stuff for I said Charlotte, not Charlotte. What are you? Okay, anyway, so I'm gonna talk about the color of stars. So the color of stars, our objectives in this mini little section is to compare the relative temperature of stars based on color and understand the use of color indexes to measure the temperature of a star. So this right here that I'm blocking again, oh, that's awkward. So this right here is the stars in the Sagittarius. It's in the Sagittarius star cloud. And the colors that we see, there's a bunch of them, right? So like, what colors do we see? Well, we see orange. I see some blue and some white, some yellow, some red. We see a lot of these different colors, right? Some of them might even have a little bit of a hue of like a greenish hue, but I don't know if that's just the way it goes. Now, the thing is, why are all of these colors not the same? Why is that? Like, what causes all these different stars to have different colors? Okay, well, they're different colors because it's all based on the temperature of the star. If a star has a certain temperature, it's going to put out different amount of energy. Now, to define color, astronomers have devised quantitative methods for characterizing the color of a star and actually have used that to determine the stellar temperatures that are given out. So, color and temperature. Now, this guy named Wine, he came up with a wonderful law, and we actually use his law to relate stellar temperature with the color that the star is. So we have blue colors, and that dominates the visible outputs of very hot stars. And then red happens to be our cold color. It dominates cold stars. Now, I want you to understand a cold star is still hotter than anything that you could possibly survive, but still, it's cold in comparison. So the question is, why is this? Why is all these things? And not necessarily. Some stars get colder as they age. That is true, but there are still like, it's like an age range, right? And so there are still like a white dwarf is incredibly hot, but it's at the end of its life cycle. And so not all stars actually are based off of that. It's actually based on the amount of energy that they're outputting. Now, they could be putting out less energy when they grow in size, which happens due to aging. But if they implode upon themselves, like a white dwarf usually does, it's putting out a lot higher of energy. So it would not necessarily, it's an older star, but it's a hotter star. Now, why is blue the coldest and red the hottest? Well, so we have this thing called the electromagnetic spectrum. It's our list of colors and everything like that, right? So on the one side, we have radio waves, and on the other side, we have gamma rays. And it goes through all these other ones. And in the middle, we have our visible light spectrum. So we have red and we have violet, right? Roy G. Biv, right? That's how it goes. And so we have that in there. And so red has our biggest wavelengths, and they show up the least frequent amount of times. Their wave hits least frequent. If something hits the least frequent, that means it doesn't have a lot of energy, right? It doesn't pop up all the time. It's not very frequent. It has lower energy. Now, blue is on the other side of that spectrum. It shows up incredibly frequently. It happens to pass by a lot, which means it's a high energy wave because it's very frequent. So if you have something that is high frequency, it's higher energy. Higher energy means more heat. That's just how it works. More energy equals hotter star boy. That's how I'm going to stay hip with the kids, by the way. So if you have more energy for something, it's going to be something that ends up being hotter because most energy is pushed off in the form of heat. My guess, I don't know. I'm not quite sure why there aren't violet stars. It might just be that they don't get hot enough to push out the color. Violet would be the best assumption I have as to why they aren't violet stars. But there are probably very hot blue stars, but it probably just does not get hot enough to create violet would be the best option, would be my best understanding. They're not putting out enough energy to do that. Now, to understand these blue stars, they have hot temperatures that are over 400,000 Kelvin. And the coolest stars, which, note, these are the coldest stars, are still about 2,000 Kelvin. Okay, so what's that mean to you? Because you're some random person that's probably in America and you're like, I don't understand what Kelvin is. So that's 71,540.3 degrees freedom height for the 40,000. And 2,000 is equivalent to 3,140.3 degrees freedom height. So that's just to show off that these things have incredible heat. Like even the coldest thing is 3,000 freaking degrees. That's a toasty boy. Now, our sun actually sits around a temperature of about 6,000 Kelvin, which in freedom height is about 10,340.3 degrees. A lot. Now, at its peak wavelength, it actually ends up being a yellow-green. And it's this nice mix of yellow and green. Now, to us, if we're in space, we see white star. It's just because of the equal amounts of light that are coming in, and we get an equal amount of all these colors that are coming and bombarding us, and it's like blah, 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 all this light. And so it's like, oh, that's pretty. It's a white star. Now, because of the nitrogen in our atmosphere, it actually knocks off a bunch of these things. It refracts all this light, and it actually makes the star look yellow, and it takes all the blue rays and refracts them throughout the rest of the sky, which is why the atmosphere is blue. Why is the sky blue? Ha! Because of nitrogen, basically. Nitrogen and refraction cause all the light that's coming through like a prism to come and bump and go through. Could it be possible for a star to be so hot that it's not visible? It could. For all I know. I mean, that we just wouldn't be able to see it yet, and so we wouldn't know. No, we actually have a bunch of. So my roommate goes, "Isn't that a weird question? Because most of our stuff goes in visible light." Not necessarily, because we actually have a lot of infrared and ultraviolet radiation telescopes, and we also have a gamma radiation telescope here on Earth as well. Yes, that's actually how we figured out that the sun has an atmosphere, and that's whatnot, because we actually figured out, and we used a UV ray We use a UV telescope to do that, which is pretty cool. So, all right. Last we have are these color indexes of colors. So, how do astronomers measure a star's apparent brightness? Well, generally, we use filters. We filter the light that's coming through, and each of these filters transmits only the light from a particular narrow band of wavelengths. And so, one of the most common sets of filters that we have in astronomy for that measures stellar brightness ends up being 3 wavelengths. One that corresponds to the ultraviolet wavelengths, one that responds to blue, and one that responds to yellow light. They're called the U, B, and V filters. Now, the brightness measured through each filter is usually expressed in magnitudes. The difference between any 2 of these magnitudes is called a color index. So, now astronomers have agreed that the ultraviolet, blue, and yellow, which is also called the visual magnitude, which is how we get our V, right? So it's ultraviolet, blue, and visual. These magnitudes of the UBV system are actually adjusted to give a color index of 0 to a star that has a surface temperature of about 10,000 degrees Kelvin, or 17,540 Freedom height. Now, the BV indexes actually of stars, they generally range from negative 0.4, which is our bluest stars, to +2, which is the reddest of stars. Our sun actually sits at about +0.65 on the BV index. And by convention, what this ends up meaning is that it takes all this blue light minus the redder light. And that's what we get. So we took all the blue light, we minus the red light, and that's what we're left with. Now, why would we use a color index if it ultimately implies temperature? Well, and that's just because the brightness of a star through a filter is what the astronomers actually measure. And we're always more comfortable when we have something quantifiable to talk about. And so we want to talk about the brightness of what we're seeing in an apparent brightness thing, right? So we want to talk about the brightness, not necessarily the temperature, but we want to talk about the brightness of the star so we can hopefully find out what's going on with the energy in that star. Which, there we go. So, in this wonderful lesson, you guys got to hear and listen and learn about the colors of stars and the brightness of stars and how astronomers use these systems and use these indexes as well. And we got to talk about Hipparchus and how he had this old system and how we still kind of use it, but we made it cool and modern and all of that. And so that being said, I hope you guys have a great day. Stay awesome, do great things, and I will see you guys on Wednesday for the next astronomy lesson.